Check it out now, y'all.
NanoHub U, online instruction.
If you remember the last lecture, we basically set up and discussed Rutherford's scattering experiment, which was performed in 1911. And the results of this scattering experiment were quite surprising because it indicated that solid matter is comprised of a nucleus, which is very, very massive, and it backscatters particles that are incident onto, let's say, a gold foil. And what we're going to do in this week's lectures is we're going to explore some of the characteristics of this nucleus. Our intent is not to turn you into nuclear physicists, but to introduce to you some of the key ideas that have been developed in about the last 100 years or so that allow you to understand the physics of the nucleus. So to begin, we're going to talk about nuclear characteristics in this lecture, and we're going to summarize some of the broad themes that that you have to be aware of in order to appreciate recent advances in nuclear physics. And a lot of the topics we'll discuss are mostly discussed in order to introduce vocabulary, right? The words are going to be different, and it's important for you to be able to understand the words within the appropriate context. So to begin with, we have to tell you that nucleons are the basic building blocks of the nucleus. And the question is, what do we mean by a nucleon? And the answer to that question is pretty simple. A nucleon is either a proton or a neutron. So all nuclei we now know are comprised of protons and neutrons. And in principle, the number of neutrons and the number of protons could be different. They don't have to be equal by any stretch of the imagination. Different nuclei, it's important to develop a simple scheme to characterize different nuclei. And this slide is intended to show you that scheme. So as an example, we consider the chemical element lithium. Right? Lithium has 3 electrons, and so therefore it's going to have 3 protons. And this particular nucleus that I've got drawn schematically has 3 protons to balance the electrical charge of the 3 electrons in lithium. And in addition, it has 4 neutrons, which also comprise the nucleus. So the proper way to identify this particular nucleus is to develop this symbolism where the subscript on the chemical element lithium, the subscript represents the number of protons in the nucleus, and that's referred to as the atomic number. The atomic mass number is the sum of the number of protons Z plus the number of neutrons N, right? And that is a superscript, right? That appears as a superscript. So since we've got 3 protons and 4 neutrons, we've got 7 nucleons. And so the superscript on the chemical element lithium tells us the total mass number, the total number of protons and neutrons in that nucleus. So this notation is a little bit outdated. I've noticed recently the textbooks tend to write this symbolism in this form, where the numbers are now preceding the chemical element, right? So it's just a slight change in notation. So in general, to summarize, the symbol X is going to represent a chemical element. There's something like 115 chemical elements in the periodic table. The subscript Z refers to the number of protons in that particular element. The number of protons just must exactly balance the number of electrons. And the atomic mass number A is the superscript. That represents the number of protons plus the number of neutrons in that particular nucleus. So as an example, right, this is carbon 12. Carbon has 6 protons. This particular nucleus of carbon has 6 additional neutrons. So this would be the way you would represent carbon 12 nucleus. Another example is chlorine. Chlorine has 17 electrons. So it's going to have 17 protons, and this particular nucleus of chlorine has an additional 18 neutrons to give you an atomic mass number of 35. So it's important for you to know how the nuclei are named and what the symbols are represent when we discuss different nuclei. The next issue is what is the size of the nucleus, and I must say there's at least 3 different ways that you can characterize the dimensions of a nucleus. And these 3 possibilities include the range of the nuclear force. We'll talk about the nuclear force in a forthcoming lecture. We can also talk about the mass radius, in other words, what's the physical extent of the nucleus that contains the masses of the protons and the neutrons. And then there's a third possibility, which is the charge radius, because the protons are charged positive, right? There's going to be some effective radius of charge, and that's a third possibility that we can use to characterize the dimensions of the nucleus. So it turns out that for nuclear matter, all 3 of these different radii are about the same. So the range of the nuclear force is about equal to the mass radius. It's about equal to the charge radius, the first approximation. And so all 3 different criteria give you roughly the same size of nuclear matter. What I like to discuss first is the nuclear charge density. This model that I'm going to describe seems to be most appropriate for lighter nuclei, and you can model the nuclear charge density by a formula which is represented in this particular form. So this is an empirical formula that's been derived, and it has 3 parameters. One parameter is rho 0. This is the charge density. This parameter R is telling you something about the radius of the nucleus, and this parameter A tells you how quickly you go from a steady value of charge density rho 0 down to 0. So A basically controls the width of this curve, right, in this region. The parameters rho 0, capital R, and A are often determined from experiment by fitting experimental data. And the important point to realize is that the charge in the nucleus is a function of radial position, has a shape that's given schematically by this blue curve, right? The point where the charge density rho is equal to 1/2 rho naught, that's controlled by this parameter capital R. So that's telling you the effective radius of the nucleus. And this parameter small a controls the thickness of this shell that describes how the charge in nuclear matter goes from 90% of this value rho 0 down to 10% of this particular value rho 0. So it turns out for this functional form of the charge density, this thickness parameter T is about 4.4 times A, and A is a number which is incredibly small. It's on the order of about 0.5 femtometers. So a femtometer is 10 to the minus 15 meters. So this charge is really packed into a very, very small distance. And that's a characteristic, of course, of the nuclear material, and it's the characteristic that Rutherford scattering experiments unveiled back in 1911, that everything is very small and very compact. So that's just a brief word about the nuclear charge density. Up next would be the nuclear mass density, and this is an interesting discussion because it's a fair question to ask what's the radius of the nucleus based on the mass that's contained. And it turns out that to a very good approximation, the radius of a nucleus is given by a constant, the mass radius of a nucleus is given by a constant R0 times the atomic mass number A raised to the 1/3 power. So you'll recall the atomic mass number is the number of protons plus neutrons contained in the nucleus, right? You raise that number to the 1/3 power, you multiply it by R0, and you've got an expression for the radius of a particular nucleus. So this parameter R0 is again an incredibly small number. It's about 1 times 10 to the minus 15 meters. 10 to the minus 15 meters is often abbreviated as a Fermi, and that's often written as lowercase f, lowercase m. So R0 is about 1.07 Fermis for nuclear matter. Once you've got an expression for the radius of a nucleus as a function of its atomic mass number, you can now start to calculate densities, mass densities for nuclear matter. And I just run through that calculation for the nucleus iron. In this particular case, iron has 26 electrons, so it's got to have 26 protons. This particular nucleus of iron has 30 additional neutrons associated with it, so the atomic mass number is equal to 56. You can calculate the mass density by just taking the mass contained in the nucleus divided by the volume that the nucleus encompasses. If you approximate the volume of a nucleus as a sphere, then the volume is 4/3 pi r cubed, where r is given by this expression up here. The mass of the nucleus is just the number of nucleons. That's the atomic mass number A, times roughly the mass of a proton, because the mass of a proton and mass of a neutron are essentially the same. You can write down an expression for R in terms of A very simply, and I do that in the next step. And what you find is that the atomic mass number A appears both in the numerator and denominator of this equation, and they cancel, and you end up with a very simple expression for the mass density, rho, in terms of the mass of the proton in this parameter R0, which is determined from experimental data. And you can then evaluate this expression for the mass density. It's independent of A, so it's telling you that nuclear matter is essentially has a constant density independent of the number of neutrons and protons in it, right? This is not found when we deal with the chemistry of elements, because the mass density of different elements is completely different, right? Mass density of lead is completely different than the mass density of hydrogen when you're dealing with with atoms of material. But when you just deal with the nucleus of a material, you get this incredibly high density of about 3 times 10 to the 17th kilograms per cubic meter. And of course, this agrees with Rutherford's scattering experiments, which indicated a very heavy, dense region of an atom, which was very small and was very effective in backscattering incident particles. The mass density, the nuclear mass density for different materials is going to depend on the radius of the different materials. So here I just schematically show you how the mass density varies for light, middle mass, and heavy mass nuclei, right? This intercept here, when the radius of the nucleus goes to 0, right? This radius is about 3.2 times 10 to the 17 kilograms per cubic meter. That's the number that we found on the previous slide. It's also useful to compare this mass density of nuclear matter to the typical densities that we encounter in our everyday life. So here I just list some typical materials that we might encounter in a given day, right? Helium, dry air, styrofoam, water, iron, and lead. Lead is about the densest chemical element that we know, and the density of lead is about 11,340 kilograms per cubic meter. when you compare that to nuclear matter, which is on the order of 10 to the 17th kilograms per cubic meter, you can see that these nuclei are very tightly packed, and there's a very, very small region at the center of each atom, which is incredibly dense. I don't know, 10 to the 14th orders of magnitude more dense than lead. So it's very, very difficult to comprehend that type of density in the world around us. It's really phenomenal. Another important characteristic of nuclei is this concept of an isotope. And this is of course a very interesting story, but it turns out you can have the same chemical element, but you can have different nuclear masses associated with that chemical element. So this is the definition of the word isotope, and this concept arose roughly between 1913 and 1920. Some very careful work by two physicists from England, Thomson and Aston, brought this aspect of matter out. They did a series of experiments which showed that, for instance, you can have 3 different isotopes of hydrogen, right? So hydrogen has 1 electron, it has 1 proton, so its atomic mass number is 1, but the total number of neutrons and protons in the hydrogen atom can either be 1, 2, or 3, right? If there are no neutrons in a hydrogen atom, that's the standard hydrogen atom that we've discussed early on in this course. It turns out you can have a hydrogen atom that has 1 neutron, 1 additional neutron in addition to the proton. So this is referred to as heavy hydrogen. It's referred to as deuterium. And it turns out that about 1 out of every 6,000 hydrogen atoms is a heavy hydrogen. It's a deuterium atom. And then lastly, it's possible that you could have 2 neutrons in the nucleus in addition to the 1 proton. Again, there's only 1 electron, so this isotope of hydrogen behaves chemically just like deuterium and the normal hydrogen. Chemically, it's exactly the same, but it has a much heavier nucleus. This is referred to as tritium, and tritium is very rare. It's you have about 10 to the 17th hydrogen atoms. One of those 10 to the 17th hydrogen atoms will be tritium. So this concept of a isotope is discussed in this slide, and it's important for you to understand that concept because it's going to have pretty significant implications as we investigate nuclear decay. The other interesting feature of nuclear matter is that we have to invent a new unit of mass to discuss the nucleus. And the reason this was done was because the nuclear masses tend to be very small. They tend to be on the order of 10 to the minus 27 kilograms. And so rather than carry around that unit of 10 to the minus 27 kilograms, it's useful to identify or to define a unified mass unit, which is given the symbol small u. And this definition leads you to 1 unified mass unit U is equal to 1.660540 times 10 to the minus 27 kilograms. So the immediate thing that you pick up with when I write this definition down is the number of significant digits that's contained in this definition of U. And this means simply that you have to be very precise when you do these nuclear mass calculations. So for instance, you can no longer approximate the speed of light by 3 times 10 to the 8th meters per second. You actually have to go in and use the exact value for the speed of light, and that value is 2.998 times 10 to the 8th meters per second. So for instance, if you want to calculate the energy that would be released if you turn one of these unified mass units U into energy, we go back to Einstein's equation, E equals mc squared. The equivalent energy contained in this mass unit U has to be calculated by using the exact speed of light. And when you do that, you find out that one unified mass unit is equal to 931.5 million electron volts divided by c squared, okay? If you happen to use 3 times 10 to the 8th meters per second, this conversion would give you a number about 933.7, right? So this is wrong. The 933.7 is wrong. This is the accepted value. And because these masses can be measured with very high accuracy, right, you have to be aware of this. So please use this conversion between mass units and electron volts, which is derived using this exact value for the speed of light. The question is, why is this definition put forward? Why is this mass unit defined in this way? Well, it's defined in this way because it then makes the mass of carbon-12 exactly equal to 12.00 mass units. So the argument is carbon-12 is possibly the most common element that can be found in a laboratory. And if you're trying to develop a standard of mass, carbon-12 would be a very good candidate for a mass standard throughout the world. And so for this reason, you take 1/12 of the mass of carbon-12, and that leads you to this definition for the unified mass unit U. So with this definition for U, you can now write down the mass of a proton, you can write down the mass of a neutron, and you can write down the mass of an electron in terms of these new mass units U. Right? You can see that the mass of the proton and the mass of the neutron are slightly different. Right? The mass of the neutron is about 1 part in 1,000 heavier than the mass of a proton. And of course, the mass of an electron is about 1,800 times smaller than either the proton and the neutron mass. So we'll make use of these definitions for the mass of the proton and mass of the neutron and the mass of the electron in the next 10 or so lectures. And so it's important for you to know what those values are. The next general topic is a general discussion of how tightly these protons and neutrons are bound to the nucleus. And I want to motivate that discussion by considering the deuteron, which is the simplest compound nucleus that you can imagine. The deuteron has 1 proton and 1 neutron, so its atomic mass number is 2, right? And the question is, how tightly is that neutron bound to the proton to form this deuteron nucleus? Well, it's a very interesting story because you can measure the deuteron nuclear mass, right, quite accurately. You can also measure the deuterium atomic mass. So the deuterium atomic mass is the mass of the deuteron nucleus plus 1 electron to form the hydrogen atom, the heavy hydrogen, right? So the difference between the atomic mass and the nuclear mass is just the mass of the electron that's been added. And so this is an important idea because it's going to keep coming back over and over again. You have to be able to distinguish between nuclear and atomic masses, right? And the difference for the case of the hydrogen atom is just the mass of 1 electron. So you can do a very simple calculation by comparing the deuteron nuclear mass to the mass of the proton plus the mass of the neutron, right? That's a really interesting calculation to think. And it turns out the mass of the parts is more than the mass of the whole, right? So by that, what do I mean? I mean, if I take the mass of the proton plus the mass of the neutron, I add them up here, right? I get 2.015941 unified mass units, right? But if I measure the mass of the deuterium nucleus, if I measure that experimentally, I only get 2.013553 unified mass units. So the individual proton and neutron is actually heavier than the mass of the deuterium nucleus. And the question is, how can that possibly be? Well, without Einstein's E equals mc squared formula, that would be a real puzzle. But the argument is that the mass of the deuteron is equal to the mass of the proton plus the mass of the neutron plus some lost mass. That lost mass is converted into a binding energy B, right? And so the point is, this system here, when the neutron and the proton are very close to one another, this system here is actually more stable than the proton and the neutron separated far apart from one another. So the argument is that this lost mass is converted to a binding energy, and the binding energy is just this loss of mass delta m times c squared. And I do that calculation in the next slide, right? And what I find is there's about 3 or 4 steps associated with the calculation. I mean, first you have to start off with this mass balance equation. The lost mass is interpreted in terms of a binding energy. It's conventional to add an electron to both sides of this equation. The reason you do that is because it's much easier to measure atomic masses than it is to measure nuclear masses. So by adding an electron to each side of this equation, you convert the deuteron nucleus to the deuterium atom, and equivalently you do the same thing on both sides of the equation to keep the masses balanced. So what I do is I tend to invent a notation, right, where the atomic deuterium mass is represented by the capital M, where the nuclear mass of the deuteron is represented by the small letter m. And by adding an electron to both sides of this equation, I convert the nuclear masses to atomic masses. And again, the atomic masses are what you can measure experimentally. So you end up with an equation that looks like this, right? And then you can put in numbers, right? You can actually put in numbers, and you can calculate what the mass difference is between the deuterium atom and the hydrogen atom, which is comprised of a proton, neutron, and an electron. And what you find out is that this binding energy is about 2.22 million electron volts. Right, so this difference in mass that we uncovered between the deuteron nucleus and the proton and the neutron, that difference in mass converts to this 2.22 MeV over c squared binding energy. And what that just simply means is that if you consider this very simple experiment where you have a proton fixed at the origin and you bring a neutron in, right? And you let that neutron start to interact with the proton to form that deuteron nucleus, right? When the proton and the neutron become very close to one another, on the order of about 1.3 Fermis, right? There's a strong binding that occurs. A quantum state appears in a quantum well, and that quantum state is about 2.2 MeV below the energy of the system when the two particles are far apart. So the idea that these nuclei bind to one another and form a lower energy state, that's a characteristic feature of all nuclei, and it turns out that binding energy is going to be very important for deciding whether a nucleus is stable or unstable. So this binding energy, again, just tells you how the final state of the neutron, what the final state of the neutron is with respect to the state when the proton and the neutron are far apart from one another, right? The state is negative, it has a negative energy because the neutron is in fact bound to the proton to form this thing we call the nucleus. So that's a real quick introduction to some of the common features or common characteristics of nuclei. We'll come back and use these concepts in later lectures. And in particular, the next lecture, we're going to discuss the strong nuclear force. We're going to try to uncover some of the fundamental features of the force that holds these nucleons together to form this nucleus, which is localized in a very, very small region of space. So come on back and listen to that lecture, and we'll tell you a little bit about nuclear forces.